So we look at inverter today. Inverter is a basic device which complements the input. If you have a low input, we get a high output. If you have a high input, we get a low input. So to understand or to quantify the operation of an inverter, we utilize what we call its voltage transfer characteristics. So the voltage transfer characteristics tell us that how the amplifier would behave and what would be the function of various voltages, input voltage on the output voltage. So for example, this is a circuit which implements the inverter operation, and we are using a pull down network and NMOS. And we know for NMOS, we have to, when we don't have, and so we go back to the concept of drain voltage and the gate voltage concept here again. So when we apply a gate voltage and we get it to operate, so it starts conducting. So applying input would make it conduct. And that's what we use to our advantage in an inverter circuit. So what's happening here is for a logic 0 input voltage is close to 0. And when that happens, and especially it's less than the threshold voltage. So in that case, the transistor is off and the drain current is 0. And the output voltage is whatever is the power supply that's given to it. And that's at the output is logic 1. So here at input voltage 0, now you have the voltage transfer characteristics. We have output voltage on y-axis and input voltage on x-axis. Now, the other parts of this voltage transfer characteristic will become evident why they're important. But let's just start with simple. When the input is 0, your output is high. Now, if you have a logic 1 input, which would mean that the input voltage is equal to VDD, this case, the transistor will start conducting and it will operate in the triode region. And that's the point D on the voltage transfer characteristics, this which was pointed, and the output voltage would be, now we look at the output voltage, the y-axis, the output voltage would be 0, which is logic 0. Now, if to use it as an inverter, we would use the extreme values of the operation, where either it's completely 0 volt or it is equal to the supply voltage. And if you think about it, this is exactly opposite to what we would do in an amplifier. In an amplifier, we want to restrict our operation in this region, almost linear region. So we can then have our output follow our input. So in case of inverter, that's not the case. We want to operate it at the highest input voltage and the lowest input voltage possible. So the digital circuit has this non-linearity that we want to use, where it cuts out or it is completely just close to saturation, but not at saturation. So this region and this region is where we want to operate our transistor. Now, if we are not using a linear region, that's something which is unnecessary for us. So for us, then it's more important that our transistor has behavior which can be depicted by 3 straight lines. And in this case, the VTC is approximated by 3 regions of operation. And if you think about it, we are now breaking down the input voltage region into a few segments. So we'll look at these. What are these? And at the output, we still 2 things that we need, a high or a low as a result. Now, if you look at it, the output high voltage, which is this level, it does not depend exactly on one value of our input. Instead, this has a broader range of input value where it still maintains the high output. So if I say that on the input level, I have a broader range of voltage that I can have, and I can still get output as a high. So what does that mean? It means that my output high does not depend on the exact value of my input voltage, as long as my input voltage does not exceed the value which I have labeled here as VIL. So you with me so far? I cannot see some videos. Matt, Matthew, Alyssa, Nestor, I cannot see you. But these have important implications when we are designing a digital circuit, or what is the operation of inverter is the simplest. So we'll go to the other ones later on. So my high output does not depend on the exact input voltage, as long as it does not exceed this level, what we have denoted as VIL. In a similar way, when my input voltage exceeds this value VIL, the output starts decreasing and it enters into the extreme region on the right hand side. And after coming through this amplifying region, which is also got transition region written here, it gets into the low voltage. So we can then see that how far the output stays high or low is a parameter of this voltage transfer characteristic of the circuit that we would implement. And this VTC then helps us see the operation of our device. And we can say that for example, the high output depends on the maximum value of the input that we can afford, while it would be still interpreted as a zero input. So it gives a bigger kind of playing room or wiggle room for us. And we'll see why is this important, especially when we talk about noise or when we talk about multiple inverters or logic gates hooked up in a circuit. So the same holds on the output low, that it does not depend, the output load does not depend on the exact value of the input. So remember, this is input. And we have a range of input that we could have. And this VIH is then an important parameter, which means that my input has to be at least VIH. And as it goes above that, all the way to the value of VOH, which is VDD, what we call as VDD, the power supply. So don't get confused why it says VOH here. VOH is this. All we are saying is that this is the maximum voltage, which is the power supply that would show up as the output. So that's what you have to overcome in your input side to make it conduct and hence get a logic zero. So please stop me if I go too fast. I want you to follow the concepts here, because that directly then gets into, we define relationships and we use those to then solve the design problems. All right, so in case of low output, then we have a range of the input voltage. Again, let me clean to emphasize, between this region that would give us a low output. So here then VIH and VOH are important parameters of an inverter VDC. VIH more important than VIH. So VOH, we know that at the extreme case, it's going to get to that point, it's going to be high input, and that's going to result into low output. But now this level is important. So we can say that it's the maximum value the input can have while being interpreted by the inverter as representing a logic 1. So these 4 parameters are that important, especially when we talk about noise margins of an inverter. And that's the idea that if I have multiple inverters and there's the output of first inverter is coupled to the input of second inverter, and in the process, if there any noise that gets introduced, how does that affect the operation of the second inverter and subsequent circuit? Now, looking at the insensitivity of the inverter output over a bigger range of input, let's see what I mean by insensitivity. So for one level, high level or low level, this insensitivity, that for a bigger range of input, my output is not feeling that. So it's insensitive to some fluctuation on my input voltage. And same is for the, and when I say input voltage, I'm talking about both high or low. So that insensitivity of the inverter output to exact value of the input voltage gives me a bigger playing field in the digital circuits as compared to analog circuits. So analog circuit would not have this kind of insensitivity, or small fluctuation in the input would result into fluctuation on the output. Now, this insensitivity can be big benefit to us when we are talking about a digital circuit where one inverter is driving the another inverter of similar kind, like shown here. Now, in this case, we give a value Vn to the noise value, so which means that for the second inverter, my input has now a factor added to it, which is the output of 1 plus Vn. And we are taking it in general. It doesn't matter if it's a positive noise or negative noise, but we can define it as that this is what's seen as the second inverter as part of its input. Now, here again, if we go back to the VTC of an inverter, my in and we look at this same now with the point of view of the second inverter. So here, as long as this added noise to the input signal keeps it below this VIL. So we can think of the case that the VOI, the output of the first, is at the lowest level, at a lower level here. So we see that inverter 2 is still driven by the logic output 0. Right? So, which means that G2 will continue functioning properly as long as its input does not exceed VIL. So, which means there is an upper limit we are putting on the noise. So we can then say that Vn can be as high as the difference of these two. Right? So far with me. So the noise that we are introducing, or coming, not we are introducing from the system, G2 can continue functioning properly as long as Vn is as high as VIL minus VOL from that transfer characteristics. So we can say that G2 has, the second inverter has a noise margin for low input, and we call that noise margin on the lower side as VIL minus VOL. So we have to connect this idea with the transfer characteristic, that this can have maximum value of VIL minus VOL. Now, so we'll stick to that. And on the higher end, again, if VOI is equal to VOH. So that's the extreme value. We can again say the G2 will continue to see this as high input. Now this is input is low. Sorry, input is high and output is low. So this can continue operating as long as a magnitude of Vn is between VOH minus VIH. So for that case, then that's the margin of noise that we can tolerate, and G2 can still operate as it is supposed to do. All right, so are you with me on this? Right, I only see Evaristo nodding very slightly. So, all right, so give me some feedback. So now, which means that I can set higher noise margin as well, depending again on the VTC, which would be then VOH minus VIH. So these four parameters are then important. So now we think about the voltage transfer characteristics. So these four parameters are important for us to know, because that will tell us that how robust would be our inverter. And if you think about it, in an analog circuit, this noise would directly show up in your output and take the operation away from whatever ideal behavior would be. But in case of a digital inverter, we are getting a larger tolerance to variation in the input signal. And what does that mean? That our inverter is basically rejecting noise in the input, and that noise is not allowed to further travel through to the subsequent system, and hence it's a basic advantage of digital over analog circuits. So we can also think of it that the inverter is restoring the signal back to the standard values of output low and output high. So whatever was coming here, even the noise came in, but this is going to restore this back to whatever was the output on this side, right? So even if there is a corrupt input signal, the inverter can restore the signal back as long as we are within that range of the noise margin. So these four things are important because these would define our noise margin for both high and low inputs. And when we are looking at a circuit or an implementation, and we are given the maximum ranges, we can know exactly where what would be the output of an inverter depending on the noise margin for that given system. All right, but if you think about it, we are still dealing with the analog behavior of an inverter. There is a transfer characteristics, but there are points on the slope which have -1 gain. So if you look at this is -1 voltage by voltage gain, and the slope, the steep slope tells us that the magnitude of the inverter gain is increasing and VTC is getting to the transition point from this point onward. So from this point onward to here, there is a considerable gain. So if this was part of a analog circuit, we would be getting a gain out of it. So what we want is we want this point M to be as steep as possible. So which means that we want this to go like this, but that means that this is infinite gain. So that's the highest slope that you can, infinite slope there. So there's another interesting point, which is point M, and that's the point where V out is equal to V input. So right in the middle. So this is considered as the midpoint of the VTC, and that's the point considered where the inverter switches from one state to the other. And this is what plays a big role in time delay calculation of the inverter. We will not go to that, but just to know that in a typical logic inverter, there are some critical points which as designer we want to know and keep our voltages on the safe zone. So hence these levels are important, VIH and VOH, which is shown here. So we want to switch quickly from those to the high or low states. So having said that, then this would be the transfer characteristics of an ideal inverter. And this is something where the swing is maximized, which means that we are making as quick of a swing as possible. And we also have larger noise margin here. So going back to the discussion of VIL minus VOL and VOH minus VIH. So if you think about it, the ideal case would give you much larger noise margin. And in this case now, the ideal case is that our high would be exactly the supply voltage and our low would be exactly 0 volt. Now in this case, then the midpoint is right here, which is VDD by 2. So which means that let me just clean it up a little bit. Which means that on both sides, my VIL would extend all the way to this point, and my VIH would start from that point. So it's the same central point where we would start. So which means my noise margin also would be all the way to that midpoint. So, and that's because here, this is 0 for an ideal case. And this guy is all the way to VDD. So this is to the maximum point. So we can see that in the ideal case, this is what we would want, the sharp transition. And if in this case, if we were to use it as an amplifier, we again would be infinite because of the slope is infinite. So that's the ideal case, how we would want it to go. All right, so So I've seen the question, I'll address those at the end. Now, having known the ideal transfer characteristics and the realistic transfer characteristics, how do we implement and what are the implications in there? So we implement very simply as voltage controlled switches, which means that the voltage is controlling it to be on and off. So this is the simplest way how an inverter can be implemented. What we are seeing is this blue box is the switch, which turns on and off, and that's being controlled by an external voltage. Now, if you think about it, that when it's turned off, which means that the switch is open, the signal is not going through, so you get your input, you get your power supply voltage VDD on the output. So, which we have to understand the situation where, say, when this is low, this is open circuit. And when this is high, we get a closed circuit. So when it's open circuit, we get high here. When this is 0, we get 1 here. When this is 1 here, which means we have closed the circuit, we are getting 0 here because the voltage is getting grounded, the signal is getting grounded here, and no current, the current is flowing to the ground. So, but this, what we call on resistance, there is still, this one is very high resistance, so we take it as open circuit, but this still has some resistance, what we called RDS before, which was the case when VDS was small. So we did that analysis. So that can be implemented here. So which would mean that there is some signal, it's not completely 0. So going back to the voltage characteristics, so then we can see, yes, there is some voltage, which we call as the output would treat it as the margin on the input side and still stay or still consider it to be 0 on the output. So in cases when we implement that, then we need to find the characteristics. So even the off resistance is high and open switch completely almost is approximates to open circuit. The on switch has an on resistance, what we call as R on. And that is when the VI is high. So in that case, the inverter would have, like we saw on the previous slide, that's R on and that's V out. So this would be the VDD voltage drop across R on. So there is a voltage, what we generally say that signal is grounded, but there is small resistance and hence some voltage on this side. Sorry, so this was the voltage drop on the output because of R on. So that's VOL. So even we say there's no signal, but there is some signal because of, so if you look at it from this side, it's a voltage divider. So we do have small resistance there and hence small voltage. But that's from the voltage transfer characteristic. So this still gives us a low output. All right, so that's the actual implementation of uh, an inverter, in this case a switch. And again, now this can be pull-up network and pull-down network, and we look at what would be the situation. So we have just made a blue box, and without going into what's happening inside, but we are looking at the implementation of the inverter itself. So it can be implemented with network of pull up and pull down networks as well. And this is example which is using a pair of complementary switches. Pull up connects the output node to VDD, and the pull down switch connects the output node to ground. So we have seen that before. This is on the higher side, power supply side, and that's on the pull up. What kind of MOSFET is a pull up network? I have tried to speak about it a whole bunch. What kind of MOSFET is used in a pull up network? Yeah, we have exam in probably 5 days. So this is part of that. So pull up is MOSFET, because you have to apply voltage to get it to low level. And pull down is when we are using NMOS, and pull down is when we are using NMOSFETs. All right. So let's look at what happens here. So when we are using low input, the pull down is open circuit. So we see the signal, high signal at the output, right? So this case, that's with it small resistance is showing as high. But when we have input is high, then the voltage supply is not showing up on the output. So what we have is low at the output. Now, again, there is, we can draw VTC for that as well, but the basic idea is still the same, that our output is 0 for the high, and our output high is just the VDD, which is shown here clearly. In same way, we can find the resistance, the small resistance that's shown up when we are doing this. So let's do an exercise and can look at a few implementations. So exercise 16.2. It's right from the book. Design an inverter to provide, and that's the same figure that we have seen before. I'll draw it. And here's the output, VDD. So all these are given. VDD is given as 1 volt. The RD is given as we don't know RD. We are given drain current. Okay, so we have the voltage, we have the drain current, we can find out RD, 20 microamps. We are given output voltage as 40 millivolt. The gate is 1 volt. All right. So to provide output low 40 millivolt and to draw supply current of 20 microamp in the low output state, let the transistor be specified to have VT is given 0.35 volt, mu n CMOS transfer characteristics are given as 540 microamp per volt square. Remember, we have to bring the same amperes, which I think are given the same already, but we'll have to make sure. Lambda is 0, which means no length dependence. Of course, we don't do in saturation, but if we are in saturation, then lambda would become important. The power supply is given 1 volt. Specify the required values of W over L and RD, right? So RD is unknown. How much power is drawn from VDD? How much power is drawn when the switch is open and when it is closed? All right. So first thing, the inverter operates in triode region, right? So we are now not going in the saturation. So we know which equation to use. That's number one. Number two, we will be using the small RDS situation because triode VDS is small. So this goes back to chapter 4 or 5, right? So, and this is given as hint also, RDS is small, which should be obvious to us now that we are in the triode region, not in the saturation. And that's a situation where we take RDS to be small. So RDS is the situation, RDS is this resistance. So we have the voltage and we know the drain current that's flowing through the circuit, right? So we can find out RDS, which is BOL divided by ID. Tell me if you didn't see what I just did. Where is RDS? It's drain to the source. That's from here to here. We know the output voltage because that's been given to us what we need to calculate, and drain current is the same, which is coming from here. It's going to flow through transistor and go to the ground. So that's the current and that's the voltage, and we are given both of those. So I got this from 40 millivolt and 20 microamp. Now, why do I need RDS? Because I will using my RDS relationship. This was, if you recall, that was a long relationship which had mu and CMOS W over L, which we need to find, times VD minus VD. So my RDS is 2 kilo ohms. So which means I have everything here except this, of course, that we need to find out, and I have this. So I plug in my 2 equals 1 over mu n CMOS is given as what, 0.54. W over L is, we need to find, power supply is 1, threshold voltage is given at 0.35. So I switch around things. I find my WL is 1 to 1.42. So that's ratio of distances. So no units. Now, RD. What is RD? So RD is now, because of this, the power supply and the voltage at the output, what resistance, drain resistance do we get here? So this voltage is known, this voltage is known, and we know the current here. So it's straightforward in that node. It's VDD minus VOL, which is, they both are given, and ID. Now this is what will give me the power. Oh, sorry, so power is straightforward. Power is VI. So we have VDD and we have ID. So that will straightforward, that will be the power where it's coming later on. But here VDD is 1, my low output voltage is given as what? 40 millivolts, 0.4 divided by, sorry, 0.04 divided by my ID, which is 0.02. So I get my drain resistance, 48 kilo ohm again, plus just from this relationship. Now, but the power drawn in closed and open situations. So when the switch is open, there is no drain current flowing. So if I have to do VDD ID, in this case, which is this, the gate open, sorry, the transistor open, no current is flowing through, so that would be 0. But in case when ID is flowing and ID is given as 20 microamp, my power would be VDD is 1 times 20 would give me 20 microwatt. So micro gets through here to here. All right, so same analysis, but we have to stay in triode region, and we have to know now with respect to my voltage transfer characteristics that which value is what we use, the lower level or the higher level, depending on the situation. Noise margins can be calculated from this information. We have a complete picture of an inverter and whatever is happening in its operation.